So without any further ado, I want to introduce you Chris Neugebauer for all that he's done in the community, his first keynote address here at Kiwi Pycon. Thank you so much.
Well, that was a welcome. Thank you for that. So I got this message 13 months ago now, deep in the darkest moments of the pandemic and the border closures, and the hope of popping over to Australia, quarantining, and using the Trans-Tasman bubble as an excuse to come visit New Zealand was a real moment of hope back in July last year. And obviously that didn't happen. This conference in February didn't happen, but my keynote offer remained, and I'm so grateful for the opportunity from Carlos and Danny and the rest of the Kiwi Pycon organizers for this opportunity to talk to you all. It's a real honor to give this talk here at Kiwi Pycon. So I have been working in Python for what feels like a very, very long time now. And for most of my career, I've been working in languages that weren't Python, and I've had to find ways to sneak Python into my day job, and getting kind of annoyed if I ever ended up using a language that wasn't as expressive as I found Python to use. And in those jobs, I've ended up with somewhat of a reputation as a Python apologist. And even now, I'm spending a lot of my time thinking about why I like Python, what things Python could be doing better, and that's what most of my talks tend to be about these days. And today I want to revisit a concept that I spoke about last at a talk I gave in 2019 at Pycon AU. Firstly, because I did not spend nearly enough time dwelling on this particular idea, and secondly, because the Harry Potter reference in the title just is not a good look these days. And perhaps most importantly, because I made some really bold assertions in that talk that got proven wrong within 2 major versions of Python. And I would much rather my discussion of this subject to be timeless. Okay, so as a deeply committed Python apologist for more than a decade, the moment that Python has found itself in is a bit weird to me. Who here has seen this acronym before? Okay, so for those of you who haven't raised your hand, this is a Dutch organization, and they publish an index of how important they think programming languages are at any given moment. And I'm unsure of how their method works, but they've been doing this for 20 years at this point. And they're the ranking that people seem to take seriously, so who am I going to argue with them? Especially when, late last year, they said that Python is the #1 most important programming language in the world right now. And even this month, their headline is, Python is going through the roof. So today I want to talk a bit about why I think this might be the case, because depending on where you observe the world from, this might be a surprising thing or an unsurprising thing. So when I was wrapping up my first Pycon AU, which was actually 10 years ago yesterday, I realized, the #1 programming language on TIOBE was, of course, Java. Or I guess maybe C, it really depended on what day of the week you were looking at the graph at that time. But while I was definitely a Python guy, my career found me and a lot of other people around the world programming in Java. And 9 years ago, I got to watch Jacob Kaplan-Moss, who at the time was the head of security for Heroku, and he gave a talk at PyCon Canada. And at the time, Heroku, it was popular, it was well-maintained, it was relevant, and it was a great place to observe the worldwide developer community's trends. And he asked the audience of 500-odd Pythonistas what they thought would be the most important emerging language on Heroku. What did we think this was? Yeah, no, it wasn't that. Wasn't Java either. It's now 2022, and the answer should be slightly more obvious to all of us, because Heroku, it's a platform for developing web applications or services, and the fastest growing language for web in 2013 is now the most popular programming language for web work right now. It's JavaScript. It was actually server-side JavaScript he was talking about, specifically Node. And it's a fair prediction. Like, TIOB showed that JavaScript was catching up to Python by the very end of that year. If someone said to me in 2013 that Python would be the #1 programming language in the world in 8 years' time, I'd have guessed it would have been thanks to Django and Flask, because it would make Python the best choice for web development, and Python would be popular because of the web, because Python in 2013 was a web language. And I think most of us missed the other thing that happened in 2013, back in 2013, which is that a major library became fully Python 3 compatible for the very first time. And this was 5 years after the first release of Python 3, mind you. And it happened even 5 months before Django had their first preview release for Python 3. The libraries that became Python 3 compatible for the first time were SciPy and NumPy. No longer having to focus on adding support for Python 3 meant they could actually innovate on features for the first time in a while. And it meant that the scientific Python community was able to spend their time paving the way for making more scientific libraries available to scientists who use Python or who might want to use Python. I don't think that anyone here would dispute that the success of Python in the scientific world is a big part of the reason why Python is as popular as it is today. I think we all agree, like, Python gives us good tools that let us complete the jobs that we need to do. And if you're a scientist or a data analysis person, that's data analysis tools, machine learning libraries, and these are by and large high-performance libraries written in hand-optimized C, C++, or Fortran. And these are all difficult languages to pick up, especially if you're somebody who only writes code incidentally to your job. So this is where glue languages came in. And glue language, like Python was introduced to me as a glue language all the way back in 2004, whenever it was. These are languages that are particularly good at taking several different libraries from lots of different sources and smushing them together and letting you come in and join those libraries together with minimal effort. So what does it take to be a good glue language for high-performance compiled code? Well, you need to start off with by being able to take those high-performance libraries and use those in your preferred language. And this has been a solved problem for a lot of time. Back in the 1990s, there was this thing called Swig. Who's heard of that? Okay, half the people in the room. For those who aren't in this room, basically what you do is you'd write a C file, you would write an interface description, and then Swig would basically spit out bindings for TCL or Perl or Java or C# or JavaScript or R or MATLAB or any other language you could think of, including Python. Any language you wanted to use to drive your library, you could use Swig, it would do it for you. You get good enough bindings basically immediately. Bindings are easy, but if simply being able to use libraries was sufficient, I genuinely don't think there'd be anything that would approach the consensus that we have now about what languages people use in given domains. Did my microphone just change? So it's not enough for you to just be able to write code against a library. You need to be able to express your ideas in a way that makes sense in your field. So I'm going to talk about Python 3.5 for a while, because Python 3.5 was notable for 3 features, which I'm going to be talking about 2 of those later. The third, I think, is a useful example for what I'm going to be talking about during the rest of this talk. Who recognizes this character? Okay, so if you've written any scientific Python lately, you'll recognize that this is the matrix multiplication operator, not the decorator. This operator is important because matrices, which are important in scientific computing, require both matrix multiplication and scalar multiplication. These have quite different semantics as operators. And if you're a programmer who works in software engineering, you might be questioning why Python needs its entirely new operator to support what is in effect a niche operation that nobody really needs. And as a programmer, you'd say, okay, well, I've got object orientation, so I could implement a multiply by method on a matrix class, and that would obviate the need for having operators. But if you're not a programmer, well, suddenly you need to have method calls explained to you. You need to have operator overloading explained to you, and what the difference between keywords and named words are. And that's a lot to explain to a physicist who just wants to multiply a couple of matrices like you could in MATLAB. So I'm going to talk about Kotlin for a bit. Kotlin aims to be a successor language to Java, and they not only decide that operator overloading was good, but there also might be operators that don't currently exist in Java that might be important to people. So they give you the idea of writing an infix function, this thing here. Basically, it lets you call a function like an operator, and this is great. Anytime you need to make your code easier to read by using an operator, you can define an infix function. So if you've got an important library, you could use Swig or something like it to make your Java bindings. You could slap some Kotlin infix functions on top of those bindings, and you have a scientific library that gave you things that looked like operators, and that should have been enough for Kotlin to dominate the scientific computing world, which we all know happened. So infix functions, they solve one of the two problems with method calls. The first is that you can have operators for things that people think need operators. You don't have to explain why scalar multiplication deserves an infix operator, but matrix multiplication needs to use a method call. The second problem is one that Python solves, but Kotlin doesn't. In Python, you can always trust that the non-commutative multiplication operator will be called @. In Kotlin, it is left down to the library author to come up with a good name for the infix function. This doesn't mean that Kotlin's choice is a bad one. Kotlin's choice gives you the flexibility to define something as an operator whenever you need one, at the expense of having to choose a name for it, or knowing which name to look up if you're a consumer of the library. Python's choice lets you have an operator with specific semantics available with a predictable name. The trade-off is that the language has to choose to give you that operator. Python chose relative inflexibility here in terms of what you could express with the language, but it in turn gave people using libraries the security of knowing how to find matrix multiplication in whatever library you happen to be coding against. It told implementers of libraries that use matrices exactly how to be interoperable with their own matrix multiplication implementation. So Kotlin's choice is one called convention, and Python's choice is one called constructs, which is what I'm going to be talking about today. Convention is the idea that there will be a generally understood way of doing things, and people will generally agree on how those things are going to work. As long as your own code matches the established conventions, it's going to be well understood. Constructs are more rigid tools or structures that let you accomplish things, and if you want to accomplish things that look like that, well, you can work within those constructs. Many of Python's key main constructs come in the form of syntax. A lot of them are in the standard library as well. Most languages have a balance between convention and constructs. So, to be clear, I'm not making an argument that the matrix multiplication operator is why Python has suddenly become popular. That would be silly. Indeed, matrix multiplication only became, that operator only came around in Python after it was already clear that Python was starting to establish itself as a scientific programming language. The addition of a matrix multiplication operator showed that Python acknowledged the needs of a new and important set of programmers who could benefit from using Python, and Python gave those developers the tools they needed to express concepts that mattered in their own domain. The scientific community repaid the language by making a huge number of libraries available in idiomatic Python. And Python is popular in science, not necessarily because of Python itself, but because of this huge volume of scientific libraries, which encourages the development of more of those things. Now, what I think led to Python being in the right place at the right time to build this feedback loop was that it was a better language than most for writing good bindings in an idiomatic way. And they stood a good chance of being interoperable and easy to predict. Indeed, one of the killer apps for early scientific Python, the IPython notebook, which is now called Jupyter, came around because it was possible to interoperate a networking library and a collection of disparate scientific and data analysis libraries all in the same distribution. I think Python has been particularly successful at being a glue language and for libraries being predictable enough to interoperate. And that's come down to Python's preference for constructs over encouraging the development of conventions. Now, I don't want to spend the rest of this talk dwelling on scientific programming because I don't know a whole lot more about it. I spend my time working on build tools. This talk is a bit of a jaunt through Python's philosophical upbringing over the years, a bit of history, some comparative discussions of past and contemporary programming languages to do some contrasts, and a bit of diving through PEPs. So, I am going to start by talking about control flow. Control flow is the idea that programs will run in a specific and predictable order, and bonus points if a human can understand that specific and predictable order by reading your code. In Python, control flow is everything from the new line character at the end of a line of code through to things like ifs and loops and function definitions. And as constructs go, these are constructs, these are all things that talk about the order in which code will be executed. And like the @ operator for matrix multiplication, these are all syntactic constructs. And for a very long time, syntactic constructs were the only things that you got to shape control flow in most languages. Now, traditional control flow constructs don't account for objects like files, which have valid or invalid states for performing operations on them. You can write simple code to open a file or read or write to it, and then you can close it to make sure that everything gets written out to disk. Now, that's great if you're writing a script that only does one thing, but what if writing to your file is part of a function and an error occurs in the middle of it before you get to close the file and write everything out to disk? So here, in the early days of Python and in other languages like Java, which is what we have here, the acceptable way to handle this was through manually writing out exceptions and doing exception handling. Java had a feature called checked exceptions, so this IO exception here, you have to handle it if a method says that it throws an IO exception. It required you to handle it. It's frustrating, but it did an okay job of making sure your code was eventually going to be correct. Python's attitude was that you'd have all of the tools you needed in your toolbox to handle invalid operations, and you'd follow convention and you'd use those tools in the right place. And the try finally block, which looks like this, used mostly correctly, that's the result of that. Basically, if you remembered to use try finally and you cleaned things up in the finally block, whoever would call your function would have their code, have their file handled correctly. It would get closed, written out to disk, regardless of what exceptions your code threw inside the try block. Now, in practice, try finally blocks were terrible because nobody used them correctly. This relied on convention, and it made it easy to have situations where my files did not get written to disk or data didn't get sent across a network. Here in 2022, experience says that the best way to ensure that your files get closed properly and your stuff gets written is to have your programming language sort of enforce a structure upon you. And back in 2003, Python core considered how to resolve this problem. I know this is a Ruby logo because I'm going to be talking about Ruby now. Ruby has a language feature called blocks. Other languages call these anonymous functions, or Python might have called them multi-line lambdas. Rather than calling context handling an open file, basically the calling context passes a block into the open function here, and then open will call the anonymous block with an open file handle, plonk it into the block, and then the block will execute with that open file handle, block will finish, go back to the context of open, which will close out the file handle and return to the calling context. Python, on the other hand, decided to implement a control flow structure to guide programmers through setup at the top of a block and tear down at the bottom. And it looks like this. And this block here actually maps perfectly, more or less, to this try finally block. And the difference is it's very easy to do this thing on the left correctly. And it's very easy to reason about how it works just by looking at the code. A with statement tells you that there's going to be set up at the top and tear down at the bottom, and that's going to be going on because you've got a with statement. Now, these are both valid approaches to systematizing a code pattern that is easy to mess up. But before we got to the with statement, one of the options that was floated was the idea that if Python would have blocks, or thunks as they called it in the relevant PEP, it would be possible to write a with function that would take care of setup and teardown tasks and execute the block of code in between. Now, in his discussions for rejecting this particular PEP, a guy named Guido, who was the BDFL of Python at the time, he said, "I think I'd be slightly uncomfortable seeing a block and not knowing whether it will be executed in the normal control flow or later." Let's unpack that a little bit, because on the surface, the Ruby and the Python approaches look very similar. So in the Ruby example, we say that we want to open a file, and then there's a block of code that does some stuff with that open file. So that block gets wrapped up as an object that is provided to the open function in our original calling context, with the expectation that the open function is going to execute it immediately. So Ruby, the language, it provides anonymous blocks as a language construct. And then it leaves it to library implementers to figure out what to do with this construct. But other than trust that the documentation says exactly what's going to happen, there is nothing enforcing how the library is going to execute that block you give it. which is why you can have code that looks like this, which executes inline, in sequence, in the same thread, which looks basically exactly the same as this, which doesn't. So in Python, using the with statement, we delegate the act of opening and closing the file off to a coroutine effectively, but we never delegate the contents of the indented block of code. That's always executed at the same level of the call stack as the code before the with statement. So the reason why Ruby is scrutable in any way here is that there are strong conventions around how library functions with blocks tend to work. Other I/O classes tend to implement block-based APIs in exactly the same way. It's the existence of these strong conventions and the willingness of library developers that allow Ruby to succeed here. And there are a lot of people with strong opinions about API design in the Ruby world, I think, because of that. Ruby has a generic, quite flexible feature here that can, by convention, be used to manage contextual state. Python, on the other hand, considers contextual state to be a key concept of programming, and it provides a construct that delegates the control flow away in a predictable fashion. Now, Python doesn't think that this feature should be used to change control flow. It doesn't mean it can't be done, just that it isn't a very good idea. I'm not going to tell you how it works. See if you can guess by the end of this talk. There are clues there. So we've seen that Python is willing to build up language constructs to establish its preferred way of doing things. But features in Python, they rarely fall out of thin air. There's always going to be a motivating context of some sort. With context managers, these were built because try-finally blocks were really difficult to write correctly. And they showed up in Python because we explored the existing constructs that we had, we found the limitations, and with a bit of work, we figured out maybe, okay, they could be a bit better. And so as a case in point, what I'm going to do here is I'm going to pick apart a construct that took 15 years of Python development to emerge in the form that you're familiar with today. And to do that, we need to start with how things are now and work backwards. And so I'm also going to show off a lot of code samples in really rapid succession. They're just here to prove that things are possible. I don't expect you to internalize them. Just let your eyes glaze over and I'll point out the bits that are important here. Okay? So the thing I'm going to be talking about is async and await, which are code constructs that are designed to make it easy to reason about which parts of your code base will execute synchronously and which parts of your code base will execute asynchronously. Async functions are how Python formalizes the idea of coroutines. These are a construct that was invented in the 1960s. Don Knuth here wrote about them in his books. And then everyone immediately abandoned coroutines in favor of threads and preemptive multitasking and time sharing, as they called it at the time, which was fine until about 15 years ago, when we realized that threads didn't let us achieve web scale or something. Anyway, the emergence of async functions in Python came shortly after the async IO package in the standard library. So async IO came before async await, because the await construct in Python 3.5 is actually some syntactic sugar around this thing called yield from. And yield from is basically a construct that defers execution from one generator to another generator. And so in Python 3.4, we had async IO provisionally, and use generator functions with yield from. So you'd use a coroutine decorator instead of your async def thing, and you would call into other coroutines using yield from instead of using await. And I think you'll agree that using async and await is a lot clearer, which is why they added that feature. So where did yield from come from? Well, it appeared in Python 3.3 for the first time under PEP 380, if you want to read the context. And it emerged because it was difficult to nest generators. If you wanted to delegate control to another generator function, previously you'd need to explicitly manage passing values up and down the call stack of your generators using loops and stuff. And it's quite tedious, it's difficult to get wrong, it's difficult to write. And if you've got stuff that's returning a lot of things, this execution pattern is actually really inefficient if you're managing the call stack yourself. So yield from, which is a language construct to enable nesting of generators, this was the feature where writing an async IO library became really, really obvious. But yield from didn't need to be a syntactic feature. All yield from does is manage a stack of generator coroutines for us. So we don't need to traverse down the entire stack of generators every time we need a value from a delegated function. And to prove how simple this is, the code to do all of this fits on a single slide in its entirety. It doesn't handle send and throw, but you could do that. You just need to make a few changes here. So there was nothing stopping async I/O from happening in any version of Python from 2.5 through to 3.2 onwards. The constructive generator-based coroutines were already there. If you didn't need nesting, and if you needed nesting, well, you could write a library to help you do that. And so Python 2.5, again, it introduced the yield expression, which is the thing that made coroutines possible. And this happened because some people realized that the generators that we already had looked a lot like these things from the 70s called coroutines, which again, people have not really thought about between those points. And in a small concession to those people, hi Nick, they added that feature to Python to shut them up. Before that, generators really only gave you the tools to emit objects out of a generator and not to send objects back in. Okay, but Python is an object-oriented language, and it doesn't have particularly strong opinions when it comes to the mutability of data. So this coroutine mix-in, which works in Python 2.2, it manages a generator API for you with the send and the throw methods on your generator API. And basically, as long as you define the coroutine inside a body method here, and as long as you remember to inspect the slot value after each time you yield something, it's basically the same as using a yield expression. It's a bit more awkward, but it's basically all the same there. So with a small amount of work, we've implemented the language level tools that we needed to make async I/O work, and it would have worked back in Python 2.2 at this point. So clearly we didn't need to wait until we got async await. So what could we do before we had generators? Well, generators make it easy to maintain the suspended state of a function. And this means a few things. It means holding on to all of the local variables. It also means holding the position of execution within a function. But more importantly, you need to be able to restore that state. So, yeah. Python 2.1 introduced debugger hooks, which allow you to set a trace function and set the instruction pointer and to set the values of local variables within a given stack frame. Okay? So with that, we can write a suspendable mix-in class with a yield method inside of it. And we have some machinery to detect whether that yield method was called. And this would work in Python 2.1. So clearly, if somebody wanted it, we could have had a recognizable version of async I/O as early as the 15th of April 2001. Now, just for clarity's sake, I'm now at the point where I think stumbling across a coroutine-based asynchronous programming toolkit would have been really unlikely. But all of the tools were there if only someone had decided to make it happen. For context, the people who cared about async I/O at that time, the Twisted people, their first release was in October 2002, and needless to say, the API that they came up with did not resemble coroutines in any way. So looking back with 21 years of hindsight, you can draw a straight line from sys.setTrace to async I/O. But that didn't happen. Coroutines were an abstract idea that we forgot about for 40 years until somebody made generators and Nick realized they were coroutines. In Python 2.1, your choices for asynchronous programming were to use threads, or if you didn't particularly want the performance hit of threads, which Python has because of the GIL, you could have used callbacks, which in Python are a terrible construct as far as maintaining cognitive overhead is concerned. So async programming, it's hard, okay? People want tools that give them the smallest amount of conceptual overhead possible to make concurrent code. Discovering coroutines with setTrace and our shoehorned two-way construction communication slot and our hand-rolled yield from implementation and an I/O library on top of all of that, it wasn't going to happen. We got threads, okay? We had threads. They're easy to understand. And if you had a concurrency pattern that didn't suit the GIL, hey, you'd use Java. And threads in Java were fine back then, okay? They're fine-ish now. Like, we just use threads. So these days we have a great toolkit for async programming in Python that is as scalable as any other language. So how did we get to this point? So we started with settrace, which exists to make debuggers in Python possible. And debuggers need to make it possible to suspend and restore execution state. Now, before Python 2.2, we had for loops in the language. They've been around for a long time, but they were limited to things that implemented getItem and index error. For anything where you couldn't implement getItem, so non-sequence objects, if you wanted to use that in a loop, you would need to either use a while loop or you would need to have a method that would splay your structure into a list. And this is why dictionaries have the keys method. You could call keys, and in Python 2, that would return you a list, and you could use that list in your for loops. There's no convention built around what you should call methods like keys on other containers. You'd need to look at the documentation for any single container type you wanted to do a loop over in order to figure out what method you needed to make it work with a for loop. So Python 2.2 introduced the iterator protocol. And the iterator protocol is machinery that lets you iterate over any sort of structure, even if it doesn't implement getItem. So Python core said, this is great, I'm going to use iterators everywhere, but writing your own iterators was still quite difficult. And so at the same time, they came up with generators, which took this idea of suspending execution state, which was possible manually with settrace, and using this to manage iteration state. It made it very easy for people to write their own iterators, and iteration suddenly became a good idea everywhere. One example of this is that Django's streaming ORM that didn't need to load everything into memory first, that used iterators, it started being developed in 2002, 2003, alongside iterators and generators. And on the concurrency side, people in Python were still using threads. So by Python 2.5, the try finally construct had been around for a while. People saw its limitations, and Python started investigating context managers. Context managers had a protocol that you could implement inside a class, but like iterators before them, the protocol is difficult to handle manually because there is state to deal with and exceptions and things like that. And this is something where the state suspending features of a generator could have been really, really handy here. But you needed to be able to send an exception back into the generator if you did a case where the block that was being context managed didn't clean up properly. And this was a great use case for the coroutine. And so context managers and the yield expression, it made them easy to use. And so they were added to Python within 3 days of each other. The with statement and the yield expression, basically the same time in history. And at this point, Python had its basic coroutines, and we started on our 10-year journey towards having async and await and async IO. Now, between Python 2.5 and Python 3.3, a few other things happened. The first bit is that multiprocessing got added to the standard library, which showed that people really, really, really wanted async programming to be easy in Python, even if that meant using operating system constructs to do it. We got the concurrent futures package to actually make it easy, but still inefficient in its own ways. And outside the Python world, Node.js happened. It had its first release in about 2008. And the subsequent popularity of Node.js showed that people really, really, really wanted cooperative asynchronous programming if only your language would make it easy to do it. But also in 2008, my friend David Beasley made this point. Still, Node.js happened. People didn't understand the Python feature that made it possible. Anyway, we had everything that we needed as of Python 3.3 when we added yield from. There were language constructs that made it possible to write asynchronous code as expressively as you could write threaded or multiprocessed code. And we got async IO by 3.4, but there was this small issue of everything being wrapped up in language constructs that were designed around iteration. And so they added async await, which in the grand scheme of things was a very small step in the evolution of Python, but it was built on a series of incremental changes that began all the way back in Python 2.1. Each change brought a feature to Python, the community explored the limitations of it, and when Python core decided that overcoming those limitations was actually going to be a valuable thing through the PEP process, they introduced new constructs into the language rather than allowing various parts of the community to come up with their own solutions to the problem. So the result is that there is now an obvious way to write asynchronous code in Python, but also that the programming constructs we have are now both obvious and an accepted part of Python. And indeed, they're so obvious that JavaScript has stolen those ideas as well, and Kotlin. So context managers, generators, and coroutines are all examples of things in Python where we didn't previously have good tools to solve a problem. These all solve problems because the community needed to develop conventions around the proper use of these constructs, and these constructs existed previously. So I'm going to talk about dynamic typing now because it's a great example of where the community rejected constructs in favor of developing conventions. And for those of us who've been around Python for a long time, we might remember dynamic typing as one of the things that actually brought us to Python in the first place. Yeah? Yeah, a lot of nodding here. And that's because back in the early days of Python, dynamic typing was seen as the way to achieve expressiveness over something like this, Java. It's one of the first languages that made a real effort of making types actually possible to understand. Java, get a picture in a moment, okay? Java requires you to declare all of your variables to have types, and for you to understand that your code use those types in a conformant manner, whatever using types in a conformant manner would mean. And it gets repetitive. Look how many times I need to say something is a string here. I don't even have to do that once in Python. This gets in your way, right? And so languages with types depend on a concept called polymorphism. And two types are polymorphic in a given programming language if objects of those two types can be used in the same context. So Java offers polymorphism by subtyping, or what type theory nerds call nominal polymorphism. And nominal polymorphism says that two types are polymorphic if they declare a common supertype. If two classes implement the same interface, well, they can both be used in circumstances that expect that interface. And Java puts the choice of whether types are polymorphic in the hands of the people who create those types. Now, on the other end of the scale, we have Perl and languages that were influenced by Perl, which have this whole weak typing thing going on, where scalar variables could become different types depending entirely upon what context you use them in. And this would save you from doing a lot of manual type coercion, which is great if you're writing a one-line script. But it doesn't stop you from performing undefined operations that might result in errors. And in PHP's case, you kind of don't find out until much, much later. So Pythonistas looked at both of these things and said no. And back when Python was young, the popular and non-academic options for typing meant that having a language that would get in the way of writing, you could either have a language that would get in the way of writing code that you could see at a glance was correct, or you could have one that wouldn't speak up at all, even if you made simple mistakes. Okay, I'll just wait for a moment. Okay, got it? Great. So Python shows the strong typing of objects, which prevents a large class of mistakes at runtime, but dynamic typing of variables, which shifts the responsibility of avoiding those mistakes onto the programmer. And this actually works quite well. We get structural polymorphism out of that, which is the idea that if you've got objects of two different types that implement the same attributes, the same methods, then those are polymorphic. And we call this duck typing, which is the idea if something walks and looks and quacks like a duck, then it's close enough to a duck for our purposes, and we can continue. So duck typing is a convention. It's a convention that Python programmers collectively developed as a community. And it wasn't the only possible convention that we could have developed at the time, but we decided that being able to do a thing is more important than just saying you're able to do the thing because you've named a thing something. And again, we have strong typing, and we have the information to look at those types at runtime, so that we could have written a runtime subtyping checker if we wanted to do that years and years and years ago. I think Zope did that. But if it were a good idea, Python probably wouldn't have added it as a construct. Instead, we decided that structural polymorphism, our duck typing, was actually a better idea than checking things at runtime, and it was one worth maintaining conventions around instead of having constructs. Structural polymorphism as a convention is an idea that's only possible in dynamically typed languages, And that, as we all know, is why Python remains a dynamically typed language to this day. So what happened? So we're in a place with a name like this. And Python 3 happened because it solved a problem with names like this, which is that, or a problem that Python had with names like this, I guess. Python had two ways to represent text. One could accommodate English text and English language text only, and names like that, and the other could accommodate text in any language. And this is a problem because the obvious way to represent text was the way that could not accommodate English language characters. This meant that Python applications did a really poor job of accommodating non-English speakers because Unicode strings happened after most of the Python world adopted the conventions of using ASCII strings. And then worse from the language development point of view is that Python didn't have a way to represent raw data that needed to be handled by computers for saving or transmitting on a network. So the language developed another convention, which was to use strings as a way to represent data for computers. And Python 3 decided that Unicode strings would be for humans and the old ASCII strings would be for computers to use, but you'd need to shove a B on the start of your strings to say it's for computers. B stands for computers. Okay, so early versions of Python 3 included a tool called 2 to 3. I used it once and then I never used it again, and that's the experience of, I think, everyone else who has touched 2 to 3 as well. Because it was meant to make it easy to bring your code across to Python 3, but the problem is that there's no way to figure out whether a Python 2 string is meant for human or for computer just by looking at it. If you had code that talked across a network and showed things to human beings, you were out of luck. So translating your code automatically between Python 2 and Python 3 automatically was beyond the limits of what our conventions in the language could handle. And static typing was actually seen as a solution at this point. Python 3.0 knew this. It added function annotations and it said, okay, we don't know how to do function annotations yet, but they'll probably be useful at some point in the near future, and we want backwards compatibility. So before December 2008, Python core knew that there would be some sort of static typing that would be essential, and they made space in the language for it. Just didn't know what it would look like. I had a pretty good idea of what it would look like in November 2009 when Google released a language called Go. So Go took the idea of the interfaces that we had in Java for 20 years before that, and it turned this idea of interfaces on its head. Rather than interfaces being the responsibility of the implementer of a type, Go would allow consumers to define an interface, and then any of the types that implement the functions attached to that interface would become usable anywhere where that interface is usable. So this is formalizing the structural polymorphism that Python had. Like Go formalized duck typing. And the difference between Python duck typing and Go was that Go required you to describe your type before you could use it. Go took a convention that Python had been using for more than a decade and replaced it with a construct. And a few years later, Microsoft developed a language called TypeScript, which was a superset of JavaScript that added optional static typing to it. Now, while it didn't invent it, TypeScript's innovation was this idea of gradual typing, which is a type system where you can express both restrictions, but also the same lack of restrictions that JavaScript had. And you could swap between the two as you needed to. And thanks to another feature it had called type inference, if you don't opt out of type checking, and if the type checker had just enough information to figure out a type, it would use that information to verify the correctness of your code. Like you don't need to say this string is a string because it's got the quotes on it. Yeah, it's a string. You know that. The real effect of this is that in practice, you only have to explicitly specify types on function interfaces or if there is ambiguity in your code. Type check JavaScript or TypeScript only has minimal cognitive overhead compared with unchecked JavaScript. That's quite powerful. And so this sort of gradual typing here and the type inference, this formed the basis for MyPy and the typing module in Python 3.5. These use the type annotations that were present in 3.0, but actually use them in the same way that TypeScript did it to JavaScript. And the problem was that this is actually nominal polymorphism. Type checking in Python 3.5 was restricted to subtypes only. If you wanted duck typing that Python had been using forever, you would need to opt out of your type checking. Python 3.5 needed you to abandon long-established conventions if you wanted to take advantage of correctness checking from types. This is possibly fine if your type checking was mostly limited to dealing with your own code base, but less so if you're consuming libraries from elsewhere. This is controversial for very good reason. If this controversy made you ignore type hinting, though, you're really missing out now, because PEP 544 came along and fixed it. It gave us the idea of protocols. And protocols are an idea that look a lot like Go's interfaces. You, as the consumer of an API, you can define a protocol, and then if an object that you receive from a third-party module or whatever has the attributes and the methods that the protocol indicates, that you indicated with the protocol, that object will pass type checking. And protocols hit the standard library in Python 3.8. So with protocols, writing code with static type checking in modern Python should be indistinguishable from writing code without static type checking, except in cases where you could probably tolerate the possibility of errors, which is where type checking is overkill and has always been overkill, or if you're writing an interface, which is where type checking should actually be the entire point. And I actually think that we're at a point where Python's static typing constructs can fully express the conventions that we as a community spent the last 30 years developing around duck typing. And as a case in point, back when I last gave a talk about type hints in 2015, this is an example from Corey Benfield about why type checking should never have happened. This was a potential type signature for the files argument that's part of the requests API. And Corey pointed out that the number of types in this type signature were underspecified because we didn't have the availability of duck typing here. So what does requests do instead? Well, instead it gives us prose, which describes the acceptable types here. You can use files, streams, it's very, very flexible, okay? You can use it in a wide variety of contexts, and requests the library remains unannotated to this day. A few years later, though, you will find this. It's not from requests. It's from HTTPX, which is a newer HTTP library. It retains the synchronous API from requests, but it adds an async API, and the entire library has type annotations. And you'll note that the shape of this type signature from HTTPX is basically exactly what Corey wrote in his argument of why type hints were insufficient back in Python 3.5. The exact same signature worked once protocols were added. So I don't think that type hints will ever be compulsory in Python. Python is still great for writing quick scripts you write and you throw away. Type hints are a waste of time there. But if you're writing code for other people to consume, type hints are a way for you to provide verification to people who are consuming your code that they're doing so correctly. This docstring again. It describes what would be the contents of a type signature, okay? Requests documents everything like this, and it has its own conventions that describe types using English language prose. Requests has a reasonably good manual though, beyond the API docs. And this is something that Python has really good conventions around. Django does it, Python core does it, but these conventions are not universally followed. People don't always write manuals in addition to their API docs. With type hints, you can start to convey the structural aspects of your interface in a formal way, in ways that both humans and computers can understand and check. And this means you only have to write descriptive documentation for big picture important things like your use cases or the intent of what you're doing. You have to write less English language documentation, but the structural information that you get from type-hinted code becomes much, much clearer if you're distributing a library. So earlier I asked the idea of whether introducing constructs can overcome conventions, and I actually think that modern type hints in Python they take established convention in language and they turn it into a construct here. If you want to communicate the types that you provide and the types that you accept, well, type hints are going to do it correctly for you. And what's left as convention is stuff that really isn't appropriate for a programming language to enforce upon you. What's left as convention is the stuff that isn't appropriate for a programming language to impose upon you. And I think this is how Python has come to see the world over the last 30 years. But Python has been around for more than 30 years now, and I don't think Python has had that point of view for the entirety of its life. Back when I started using Python, people talked about the batteries included standard library, right? Like, if you had something that was of a decent standard of code and it solved a problem that like more than 3 people had, it would end up in the standard library. It would help Python become a useful toolbox that you could carry with you on basically any Unix machine. If you had a problem to solve, you could solve it with the standard library. And as a result, at the end of Python 2's life, there was a lot of extremely niche and unmaintained and irrelevant code like, I don't know, Mac OS 9 support that was in the standard library and really didn't need to be there anymore. Python 3 came out 14 years ago at this point, and Python 2.7 was end-of-life less than 3 years ago. For the vast, vast, vast majority of that time, people were sticking around on Python 2. It took SciPy 4.5 years to get to Python 3 compatibility, let alone gaining the use that we needed. And during those 11 years, people programming on Python 2, they had a stagnant standard library. And for 5 of those years, Python 3 was effectively unusable. So putting something in the standard library wouldn't lead to people immediately using it. And the world moved on during that time. The problems that people wanted to solve in Python, they changed radically. And more, the tools that were in the standard library stopped being up to scratch. URLlib2, which has been around for longer than I've been using Python, didn't work with the GitHub API because it would only send authentication requests on 403 errors, not on the 404 errors that GitHub gives you to stop enumerating private repositories. It's an important security thing. It breaks the HTTP spec. URLlib2 followed the HTTP spec. So sending authentication headers on 404s, this was request's early big feature, and requests came out in 2011. The good news is that we had the package index, and we didn't have a whole generation of programmers who couldn't talk to GitHub. And if requests got added to the standard library, which was at one point proposed by the community like as a serious option, would there have been space for HTTPX to emerge and give us the async and the type annotations that we eventually got that requests refused to do? Would requests have got that attention? I really doubt it. So how is the standard library growing these days? Well, if we go back through the What's New page in Python 3, these are the modules that have been added to Python 3 since 2014 or so, back when Python 3 development really started ramping up after the feature freeze and the moratorium in 3.2. In the last 7 releases of Python, there are only 3 modules that are not intrinsically related to how you might want to structure a Python program. There's the time zones package, very useful, stops you from using date time incorrectly. There's a numerical statistics package for some reason. And there's the cryptographic secrets library to stop you from creating private keys with pseudo-random number generators. Also useful, but not all intrinsically related to how you write a program. Everything else intrinsically related to writing Python code. There's things from packaging tools through to standardized data structures and even the really big ones that shape the way we write programs like typing and async I/O. For the last 8 years, only 3 modules in the standard library aren't entirely about how you go about writing Python programs as opposed to what your programs do. There's this huge legacy of existing standard library modules that stuck around when Python 3 came out, and the genuinely useful ones are still updated. It's clear that the focus of Python, the language, is on making a programming language that allows for ideas to be more easily expressed. The batteries that are included in Python are grid attached, basically. That's the package index job now. What's clear to me is that the additions that Python has made over the years are all geared towards managing complexity. And complexity can come in 2 forms. Firstly, there's this mental overhead that is involved with dealing with a big code base. Type hints, they save you from needing to reread documentation once you understand the point of a function. Coroutines, they save you from needing to pre-structure your callback functions, and they save you from the GIL. Data structures let you express structures with appropriate type hints without needing to write all the machinery that lets you use them in dictionaries and sets. And on the other hand, there's also the avoided learning curve of approaching a snippet of Python code in a Jupyter notebook and needing to figure out which method a given library uses to provide for your matrix multiplication. A focus on constructs reduces the scope for disagreement away from stylistic disagreements, which we all know are a waste of time, and onto things that should be actually concerning to you. So, these tools for managing complexity are powerful. As mentioned, I work on a build system called Pants these days, and we use modern features everywhere in our Python code base. And I'm an effective contributor to Pants despite having only touched it for a year ago at this point. And that's because Python does a really good job of making the shape of programs clear. I've looked at some of our code that predates those constructs, and it's gnarly. But there is a reasonable mental overhead in contributing to Pants. And I think that's true of any major open source project of a big enough size. But the mental overhead is not in understanding the Python that is used to make things work. Instead, you can focus on how the system is put together, and that's despite having a system that might well spawn thousands and thousands of asynchronous tasks in a single build run. The scope of disagreement here isn't over how to use Python's features. Our choice of event loop is like one thing that we have in the grand scheme of things. It's not a thing that influences the entire structure of the code base just because we want to change which async runner we use. This idea of reducing the scope of disagreements is something that I think has been a design philosophy in Python for a long time. But the scope of influence that the Python language has changed across the years, particularly as the standard library is stagnated and as the package index became more and more relevant here. Over the last few years, we've ended up with a language where the core developers give you the tools to write your programs well, and if you need a library to interact with a file format or an API or a protocol, you can find that on the package index. There's often more than one way to do something, and if one way isn't obvious, well, it doesn't belong in core Python anymore. And this is why there isn't a web framework or a scientific framework inside the standard library. These days, Python tells you what your code should look like, not what it does. There are multiple web communities in Python, each of whom have their own conventions about how to do things. More so than in many other languages, though, you can look at code that is written in Python in one framework and easily figure out what it does, even if you can't immediately understand how you would write it yourself. And more importantly than just the effect on Python, the language, our community embraced this philosophy beyond just technical choices in our programming language. The Python community has governance that is trusted by the community. We build constructs that help us build and grow the community that we want rather than leaving it to chance. Like Pycon US, followed by Pycons around the world, decided that people should not miss out on participating in our community due to financial difficulty, and so built the constructs to make that happen. And now it's repeatable, it's been approved year on year, and multiple conferences do it. It's built into the shape of Python conferences around the world. And it brings good people to our community who might not get a chance somewhere else. And while these programs worked, they didn't work well enough because we left it up to chance for people to find financial aid programs. I'm glad that I found it back in 2013. It changed my life. It made Pycon AU better. Plenty of deserving people didn't, because we didn't do the targeted work to make marginalized people feel like they had space in our community. We hoped they'd just notice the programs that were there and they'd make use of them. And that's why the PyLadies program gets the attention it does now. Our community raises money and we run programs to do the work to show women and other people of marginalized genders that there is space for them at PyCons and in the Python community more broadly. It means not having to guess about whether a space is safe. And it works. In Python, in 2019, a full 50% of speakers at PyCon US were not men, up from like less than 20% when I first started going to PyCon US. And then there's a matter of community standards. Thanks to hard work by people in our community, there are expectations that Python communities all share standards of behavior and actions that we encourage, and we know what standards we believe are unacceptable because we have the constructs that spell them out. Rather than leaving these things implicit, we have constructs in the form of codes of conduct and incident response teams that follow written enforcement guidelines. People trust that the Python community enforces its standards because we have the constructs in place to do exactly that. And so just as the design of our language reduces the scope of disagreement in what it takes to write Python, we set expectations around what it takes to participate in a Python community rather than leave all of that unsaid. People come for the language, and people stay for the community because it welcomes them, and we have the structures in place in our community to make sure that that welcome is a lasting one. So we have a language where we have a preference for constructs over conventions, and that means that tools interoperate. But I think we also have a community that I think understands better than most that our humans need to interoperate as well. And for humans to work well together, we need an environment that we can enjoy participating in. And Python invests and trusts in improving the tools and the governance that we have to make sure that we actually build and grow such an environment. And maybe that is why Python is finally going through the roof. Let's try and keep it that way.
That was magnificent. Thank you, Chris.
Thank you.
I love, if you've been programming long enough, you think in the way you've been programming. And one of the astonishing things that I think you've just managed to demonstrate for us is the way that we think has been shaped by constructs that have been built that we didn't really realize were decisions. We thought they were sort of organic, that they happened over time. I'm going to be pondering this one for a while. Thank you so much. Thank you again, Chris. Thank you, everyone. We'll see you back here soon.